Let's look at a mixing problem. You have a system, a mixing chamber that has helium flowing into it at two inlets, 1 and 2, and exiting from exit or outlet 3. Temperature at inlet 1 is 350 K. Temperature at inlet 2 is 190 K. Pressure is constant throughout the system. P1 is equal to P2 is equal to P3 and is equal to 200 kilopascals. Mass flow rate at point 1 is given as 0.04 kilograms per second. Mass flow rate m.2 at inlet 2 is given as 0.06 kilograms per second. This is an adiabatic and steady flow device. Always start with the general form of the first law of thermodynamics for steady flow devices. We have that written here already. Now let's look at the terms that we don't need and we can remove from the equation and simplify the equation. So we said it's adiabatic, so these two terms, so this and this, these two heat transfer terms, Q dot in, Q dot out, can be removed from the equation. Looking at the mixing chamber or device, we'll see that there is no shaft work, there is no electrical work, so we can easily remove those two terms, W dot in, W dot out. There is no shaft or electrical work. Then the next term we should look at is the potential energy term. We can scratch potential energy terms because the change in elevation between inlet and outlet is quite insignificant. No significant elevation change. The next term is the kinetic energy, V squared over 2. So the diameters can be assumed, because the diameters are not given, they can be assumed to be the same, and the change in kinetic energy can be considered to be insignificant between inlet and outlet. So no significant change in kinetic energy. Then the sigma sign, we know that at the exit we only have one outlet and we have two inlets. So we need to expand this term m dot h for the two inlets. So I'm going to do that now. It's going to be m dot 1 times h1 plus m dot 2 times h2. On the right hand side, we just have m dot 3 times h3. So this is the simplified form of the first law of thermodynamics for this steady flow adiabatic mixing problem. Now we need an additional equation, and actually the first thing before the first law of thermodynamics, first thing you need to do is to write the conservation of mass, which is very simple for this problem. Mass flow in, total mass flow in is equal to total mass flow out. So m dot 1 plus m dot 2 equals m dot 3. These are the two equations that we have. This is called the energy equation. This is called the mass equation. Now we can solve the problem by plugging in numbers. So first of all, mass equation will simplify to 0.04 plus 0.06, and the answer is 0.1 kilograms per second. That is m dot 3. So we already calculated the mass flow rate of helium coming out. Then let's say we want to determine the temperature of helium at the exit. So generally, when trying to plug in properties in the energy equation, we have to have values for the enthalpies, H1, H2, H3. Sometimes for air, we do have a table A17, that gives us H1, H2, and H3 values, because for ideal gas, enthalpy is a function of temperature only. I forgot to mention that we are making the ideal gas assumption here. which is a valid assumption. So back to calculating T3. We don't have a table for enthalpy values of helium, but we can do this. We know that delta H is Cp delta T if we assume ideal gas and also approximate solution for use of constant average specific heat. So for delta H, we can use Cp delta T, or assuming the reference is at 0 Kelvin, we can use H is equal to Cpt. Since we're using the same reference for all three enthalpies, we're going to be fine. In that case, energy equation will result in m dot 1. I'm replacing H1 by Cp times T1 plus m dot 2 Cp T2 equals m dot 3 Cp T3. Now, since I'm assuming constant average specific heat and room temperature, then I can simplify this equation a little bit further, and actually I don't need to know the value of Cp, but there is a table for Cp. I can read the Cp value, but it will cancel out. I don't need it. So the equation will be simplified to m dot 1 T1 plus m dot 2 T2 equals m dot 3 T3. Plugging in numbers, 0.04 times 350 plus 0.06 times 190 equals 0.1. Remember, this was already calculated. 0.1 times unknown T3. The answer is 254 Kelvin. Keep in mind that, just to avoid confusion, use Kelvin in this equation for temperature. Do not use Celsius or Fahrenheit. Use Kelvin. So I'm going to make a note here, temperatures in Kelvin.